Welcome to Math 32. My name is Khalees and I am in Math 32 section 6X with Julio, and this is for summer 21. And my topic today is on Brownian motion. So Brownian motion is in everything from shaking a snow globe to the stock market. So you're probably thinking, what is Brownian motion? And essentially, the basic definition of Brownian motion is the random motion of particles in a medium. Medium referring to like a liquid or a gas. So the history behind Brownian motion. First off, I don't know why they named it Brownian motion, because this guy right here, Robert Brown, in 1827, he accidentally discovered Brownian motion. What he was trying to do as a biologist was study pollen, and he put pollen into a glass of water and noticed it moving around almost like it was alive, and he went into deeper studies to figure out if pollen was alive. What he actually ended up proving is the existence of molecules, like atoms and matter, and how much they weigh. So his discovery led to Avogadro's number. It also led to a lot of Einstein's theories, his relativity theory, and Jean-Pierre actually based a lot of his work off of it and ended up winning the Nobel Prize in 1926 for his work with Brownian motion. Brownian motion is kind of broken down into two basic types of math. You're going to have your binomial distribution, and you're going to have your geometric distribution based on what you're doing. So Einstein's work is pretty complicated, especially for this class. It's got heavy Taylor series, which you use to help calculate the formulas for Brownian motion. So a lot of this work we're going to base off is Smoluchowski's theory and the simulation of Dye and random walk. Random walk is a really cool coding simulation type. And essentially this model is from the Wiener process, which is just a continuous time scholastic process, which just means like the random process with random variables. So Brownian motion is kind of hard to pin down exactly. So you're really only looking for the first movement and the second movement, because everything after that is too complicated for computers to track. So this model is derived from the same probability of pxt for displacement of a Brownian particle along x in time t. So this model uses the binomial distribution, which should probably look pretty familiar to you guys.
Here is the example of the graph, with p being the particle, x being the collisions or movements, and t being time. It starts off as a delta function with bell-shaped curve, and as the limit reaches infinity, it flattens to a smaller bell-shaped curve.
So this is what a random walk looks like, and essentially the code to this is a binomial distribution, and it's kind of predicting the first and second movements. It's random variables. It goes in random directions. To explain the coding a little better with the binomial and geometric simulations in R and Python, here's a little bit of some explanations for the calculations. So the first movement and the second movement is what we use to create BT, which is Brownian motion. It's going to be the derivative of the particle over the derivative of time. As you can see, the derivative squared of the particle over derivative of x squared, which is going to be the collisions or the movement based on the density of the actual molecule. It goes from negative infinity to infinity due to the time. Once it reaches a higher order, that's when the graph curves out to a flat bell curve. And here's the other part of it. As you notice, p of the function x comma t, which is what the graph was that I showed you earlier, of course, starting at 0 for the initial time. This is the equation here. So you're going to have that first movement at half, and the second one is going to be x squared, which is equal to 2 times the density of the time. And as you can see here, it actually relates to the last part of Math 32 that we were working on with the variance squared and our mean or mu. So this is coding for R, which is going to be for 1-dimensional and 2-dimensional. This one is a 2-dimensional graph here. We have the code up there, So it's just taking the R norm and computing it with the variable x, so the random variable. This is actually for plotting population growth. This one here is what it looks like when you have multiple things to plot, either the molecule, population growth, and here is code. I made this one a little bigger just so you can see it better. So we've got variable x with length t, which is time. This is our random variable, and we're computing our norm, and it's to the 10,000. And this is for the simulation for a best fit line. So this is actually the same as this, but this is the best fit line within this model. Coding is also, there's another big one we use. These two. This is for Python actually, not just R. And this should look very familiar to you. So this is the binomial distribution for Python code, and this is the geometric distribution for Python code. This should look very similar to what we were working with instead of it being W, I, and N, picture this as P with N and M, and a lot of it's 2 to the nth power. So here, this yi is actually just another form of random variable. So this could be anything that you're calculating or trying to figure out. So this simulation is used for like bacterial growth, for tracking COVID cases. This one is a little more complicated, and this one's actually used for the stock market. If you notice in here that we're computing the mean, and this is also variance squared. If you notice, this is what we were working with a lot. We were working with our mean and our variance squared. This is one of my favorite simulations. This is dye in water, and so here's a 3D tracking simulation. This has very advanced coding, a little bit harder to understand for this type of class, but as you can see here, it kind of just predicts the movement of a molecule as it's bouncing along the other molecules. This is in a liquid, so like I said, a dye in a liquid moving around. So you can kind of see, you really can't predict it. So which is why you only do the first and second movement of this process, because after that, it's just too complicated to predict where it's gonna go. This was Smolskowski's model and his work. He was trying to prove that the Brownian motion or the Brownian particles are actually displaced by smaller particles hitting it forward and backward, or the probability of either or. It's the probability of m gains and n minus m losses, which follows the binomial distribution with equal probability of 1/2, meaning you see the PM1n equal to the binomial n over m, which just pretty much means the likelihood of a particle being pushed forward versus being pushed backwards. The equation below is the full equation for the expected total gain, with the mu or the mean equaling the total gain up at the top. So you're probably thinking, what does this relate to? I thought Brownian motion was mostly chemistry based, but as I dove in more and understood it a little better, these are some things that you can actually use it for. So the stock market, random walk, which is the simulation I showed, stellar dynamics, which is tracking black holes, which is really cool, and tracking the probability of it moving through space and where it's going to end up and where it's going to be. You can do pollutants in the air. You can do the diffusion of calcium, so kind of like beta and alpha decay and understanding carbon, but instead it's the calcium disintegrating in your bones. You can also track the movement of holes in electrical charge, semiconductors, so there's a little bit of physics, biology, got some mathematics and chemistry in here. So there's a lot of cool things you can do with it. Welcome to the end of my presentation. You made it to the end. Hopefully you understand Brownian motion a little better. Hopefully you can see that it is truly everywhere and used in everything. Mind-blowing. And here's my resources. I just wanted a better picture for you guys to really see. And here are some links to the websites and simulations I used. And of course, thanks for watching.